Next, scientists took basically all the molecules in the universe and separated them into two major groups: organic and inorganic. It's not the type of organic that you see at the grocery store. Organic molecules are those that are based on carbon and hydrogen. Now, they can have other types of atoms integrated also, but they have to have carbon and hydrogen. And the reason why is, remember, carbon has 4 bonds it needs to form. And therefore, it can form in the long chains using 2 of those, one carbon to another carbon to another carbon. And then it has 2 more bonds it can make to oxygen, nitrogen, especially hydrogen. This makes it be able to form very large molecules. And especially important on there, not only the carbon, as many times it's defined as carbon containing molecules, but the hydrogen is important as well, because these are usually high energy hydrogens. That electron that goes around the outside of the hydrogen can be a high energy electron. It picks up energy and goes faster, and so therefore it can store energy, and later on that energy can be siphoned off and put into chemical reactions. And basically that's what happens with food and your metabolism. It makes this kind of like a bunch of grapes, where the carbon's the vine that branches off, and the grapes are like hydrogens. And you like grapes because they taste sweet. They taste sweet because they have sugar. And sugar you can burn to give you energy. So what you do in your basic metabolism, what we call aerobic respiration or cellular respiration, is you take an organic molecule like a carbohydrate, a lipid, an amino acid, and you're going to pluck those grapes off of that organic molecule, and you're going to suck the energy out of that hydrogen, and it's going to go to low energy hydrogen, and you get rid of it as waste, but now you have the energy that you put into your chemical reactions. Inorganic molecules are ones that are not based on carbon and hydrogen. And the examples they give you are H2O, there's hydrogen but no carbon; oxygen, O2; carbon dioxide, carbon but no hydrogen; and NaCl, sodium chloride table salt. And these are usually, not always, but low energy. And you can prove that, because what are 3 ways you put out a fire? If you're out camping, you take a bucket of water and throw it on it. Water is low energy, and that's why it smothers a fire. It's a lot different putting an organic molecule like O-octane, aka gasoline. Throw that on the fire. It contains a lot of energy, so why it goes woof. Carbon dioxide, how do you blow out your candles every birthday? And it's because it's low energy, it's smothering the fire, it will not burn. And if you have a grease fire, you don't want to throw water on it, and you're not going to blow it out. So smother it with salt. Salt will not burn, so it will smother the fire as well. A lot of these will form ions, so basic ions you're going to see ionic forms the rest of the semester. We already talked about H plus is hydrogen ion. It's in group 1. Sodium's also in group 1, so we'll form a sodium plus 1 charge. Potassium plus 1 charge. Calcium's from group 2, and we'll form a plus 2 charge. Chlorine is in group 7, so we'll form a negative 1 charge. And we get in some polyatomic ions. Okay, bicarbonate. Now, HCO3 with a minus 1 charge. Now, this does have carbon, does have hydrogen. This is a gray area. Some books, about half of them will put it into organics, half of them will put it in inorganics. By definition, it should be an organic molecule, but it is low energy. Another way you can put out that grease fire, throw baking soda on it. Bicarbonate. Phosphate, PO4 with a minus 3 charge, and the sulfate, SO4 with a minus 2 charge. In the organic molecules, we have the carbohydrate, aka sugar, or saccharides. They're in a ratio of 1 carbon to 2 hydrogen to 1 oxygen, usually in multiples of 5 or 6 in a ring. Their function, of course, is energy storage, and you can prove that 2 different ways. One is take a spoonful of sugar over a flame. As it starts to caramelize, starts to turn brown, then black, and starts to bubble, take it away from the flame, and it will continue to burn on its own. Okay, slowly and very little, but it will. Also, give it to a little kid. They'll be bouncing off the walls because they'll use it for energy. Now, to be honest, most biochemists and nutritionists say that sugar does not cause hyperactivity in kids. However, when one nutritionist said that, one senior nutritionist was lecturing at the college, I couldn't help myself. I raised my hand, even though they're there for the students. I raised my hand and said, "Excuse me, do you have children?" And lo and behold, "No, I don't." I said, "Want to borrow mine and feed them some sugar? Do a little experiment." Because when I give my kids sugar, they're bouncing off the walls. Structure, we don't use it too much for structure. It's mostly for things like trees and other plants. It's actual structure, a ring structure. As you see here, nice little ring structure where these meet. That's a carbon. And of course those bonds coming off of it. Notice the OHs all around it. Remember, those are polar covalent bonds. So the more OHs, the more those partial positives and partial negatives, and so will help this to float in water. It'll be suspended, attracted water around it, what makes sugar dissolve in water. And it's literally all around the molecule. This is a ring structure. It can also form a string structure if this oxygen bond up here breaks. Okay, this one breaks right here, and it'll become a string, and it just goes back and forth between the two. And monosaccharides, simple sugars, single sugars. Of course, here's the typical glucose, and here we see fructose, and here we see galactose. In disaccharides, at double sugars, here we have sucrose, which is two glucoses linked together. Lactose, which is a glucose and a galactose linked together. And maltose. Two glucoses linked together. Got ahead of myself. The sucrose is a glucose and a fructose. I was thinking of maltose. Polysaccharides are long chains of sugars. We have starch, sometimes called plant starch. That's a bit redundant because it only comes from plants. And here we see these are branched, lots of sugars linked together. And also we have glycogen, often referred to as animal starch, which long chains of sugars only produced in animals. Slightly different chemical bond between the two. Lipids, mostly known for the fats, include fatty acids, long chains of carbon with hydrogen. Phospholipids, which is a glycerol, two fatty acids, and a modified group. And also steroids. These have mostly carbon and hydrogen. And because they don't have very much, they'll just have a little bit of oxygen and phosphorus. So a higher percentage of their weight is due to hydrogen, and so therefore these tend to have twice as much energy by weight as carbohydrates or proteins. And as we look at an example here, here's a phospholipid. This is a fatty acid. Fatty acids can be saturated, like this one on top. Saturated means it's carrying as many hydrogens and therefore as much energy as it can carry. Unsaturated, like down below, means that it's missing some pairs of hydrogens. Those bonds replaced by double bonds in the carbon chain. And so if you have monounsaturated, you're missing one like here, and polyunsaturated, two or more pairs of hydrogen are missing, and you have more double bonds. In that phospholipid, you have this funny phosphate group over here attached to this nitrogen group. You see the negatives and the positives. Of course, this is a hydrophilic portion, and fats, remember, are hydrophobic, like oils. And so this molecule actually will have part of the molecule as hydrophilic and part of it is hydrophobic. And we'll see why that's important to life in the next chapter. These give you energy. They store for energy. You can burn these when you work out. Every day you burn about 5 or 10% fat for energy. Of course, if you're on an Atkins diet or something, you take in less carbohydrates, you'll burn more fat. You can also tell that when you grill out and you see the fat on the outside of the meat starts catching on fire, it burns. Energy storage, because if an adult eats too much candy, I mentioned kids run around and use it for energy to move, we just tend to store it up, so you just gain an extra pound. We use it for structure, especially membranes, we'll talk about in the next chapter, and of course steroid hormones are used as messengers in the body. There's structures, as you saw here, the strings, and here are the rings. There's a steroid hormone.